All right. All right. So I was talking about size reduction. I tried to give you some examples about the positive effects of size reduction itself without having to really worry about the quantum confinement effects. If you look at this simple problem, if you consider a sphere of radius 2 centimeters, and if you subdivide this sphere into identical small spheres, we looked at the example of a cube being cut down to smaller cubes of micron sized and nanometric sized dimensions. Now you have a sphere and of radius 2 centimeters, and you cut down this sphere into smaller spheres. The only difference is this radius of the sphere is each sphere is 2 nanometers here. So the thing is, how many spheres will be there if the total volume of the original sphere is kept the same? So that means, okay. So what will be the total surface area of the these nanospheres? A similar example we saw yesterday with respect to the cubes, right? So if you quickly look at this answer, it's very simple to do. You have the surface area of the original sphere, which is about 50.24 centimeter square, and the volume of the macroscopic sphere is 33.49 centimeter cube, and then you need to find out the volume ratio between the macroscopic sphere and the nanoscopic spheres, right? So the nanospheres are smaller by a factor of, so everything scales down by this factor. What is the factor? This factor is 10 raised to 7. So in terms of volume, 10 to the power of 21 of them will have the same volume as one macroscopic sphere of radius 2 centimeters. Okay, which means now each sphere has an area of each nanosphere now has an area of 12.6 into 10 raised to minus 18 meter square. The total surface area is 5.02 into 10 raised to the power of 4 meter square. So if you just make a comparison, this is about 10 to the power of 7 times greater than the surface area of one single macroscopic sphere having a radius of 2 centimeters. This is again just to emphasize that the size reduction itself has positive effects. I said we have seen this. One of the applications is you create these corrugated surfaces, nanostructured surfaces, and then if you have them in a coating form, this is called the surface coatings. That's where the surface coating technology is a big field now. Okay, nanostructured surfaces, surface coating technology uses the technique of making corrugated surfaces, nanostructured surfaces, and the whole idea of getting corrugated surfaces is to increase the surface area, right? So I was giving an example of a back electrode contact of a solar cell panel, where the increase in surface area by virtue of getting the surface coating in a corrugated form, right, is useful in trapping of more photons over the given area. Okay, all right. Now, we were also looking at the process of diffusion. Okay, this is a good way to explain how diffusion happens. You drop, you have a drop of ink there, and you see how it diffuses in a liquid, and this process of course in liquids is much faster compared to diffusion in solids, right. I gave you the number yesterday. The typical diffusion coefficient is in solids at room temperature is 10 to the power of minus 9 meter square per second, and that's very slow. That's absolutely so. So if these two are two different solids and made of different elements in each case, and if ions or atoms have to diffuse from one side to the other, right. So that means you will see the migration of ions at the interface leading to the formation of a new phase at the interface, and that process is going to be very slow. So ideally if if this is say a compound A and this is a compound B, and you can have the ionic species migrating from this side to the other, from B to A and A to B. Okay. This can lead to the formation of a new phase, say AB, and for this diffusion to happen in solids normally with diffusion coefficients of the order of 10 raised to minus 9 centimeter square per second, you can imagine the time required for this species to migrate through the entire solid to convert the entire thing into a new compound called AB. Okay? This takes hell a lot of time. So if there's an example, if you have magnesium oxide here, Al2O3 there. So you see the formation of MgAl2O4. So if you make a reaction happen between magnesium oxide and aluminum oxide, you can get this new compound called magnesium aluminum oxide. Okay. Now, if you start making the reaction to happen between two solids, one is magnesium oxide, the other one is aluminum oxide. Okay. And typically the reaction temperature has to be 1000 degrees centigrade, because see, you first need to break up the individual bonds in magnesium oxide and aluminum oxide, right, and the new bonds have to form for the formation of this new compound, is it not? So it's a migration of magnesium ions and aluminum ions on the other side. So magnesium ions migrate from this side of the solid to the other side, and aluminum ions migrate from the right hand side to the left hand side, leading to the formation of a new phase first here, because you're taken this, you're making the reaction to happen between say two solid blocks of magnesium oxide and aluminum oxide. So any migration of this sort can happen only at elevated temperatures, 1000, 1200 degrees centigrade. Okay. Now you see, for every 3 magnesium ions that migrate to the right hand side, you will have 2 aluminum ions coming to this side, because there's always a charge balance that has to happen. And the oxygen stoichiometry almost it's automatically adjusted, because you're making this reaction to happen at ambient, no, in oxygen atmosphere, in air rather. Okay. Now, if you leave this process to happen this way, right? If you consider these as the real dimensions of magnesium oxide and aluminum oxide, probably it will take several years for the entire length to get transformed into magnesium aluminum oxide. Obviously, 10 to the power of minus 9 centimeter square per second at room temperature. At this temperature, even if it is faster by 2 orders or 3 orders, still it takes a lot of time. So in fact, this is always taken as a good example, magnesium oxide and aluminum dioxide, because if you make this reaction to happen in a furnace, and if there is a way to visualize if the reaction is happening or not, so suppose you have a box furnace and a viewport through which you can see what is happening inside. So, so I have these two pieces kept inside the furnace, and you want to see if a reaction is really happening or not. Because especially in the case of this particular example, between magnesium oxide and aluminum oxide, the new phase that forms gives you a color change at the interface. So this can be actually seen. This is one of the examples that is used for demonstration in any material physics lab. So the effect of change of color is a well-known Kirkendall effect. You can actually see the change in color happening at the interface. Okay? So again, I have these two solid pieces. I put them together in a furnace at 1000 degrees centigrade. So when the temperature is 1000 degrees centigrade inside the furnace, I'm able to visualize what is happening at the interface. So when you start seeing the color change, right, the color change can be seen in this particular case. It may not be seen in all the cases, because the new compound that forms, which is magnesium aluminum oxide, has a different color compared to that of magnesium oxide and aluminum dioxide. So you see, if these two are compounds with say white color, if the new compound also has a similar color, you will not see the formation of this new one. Okay, but in this particular case, you can see this. So this process of converting these two into complete magnesium aluminum oxide takes several years, right? So how do you hasten up this reaction? So the best thing is you plunder it, right? Get it down to smaller particles and get smaller particles of this. So this you are doing by mechanical attrition. So the process of mechanical attrition, so you break this solid body into smaller particles. That's all. That's what you're doing. And this can be done by crushing, pounding, which is called mechanical attrition, right? Now, by mechanical attrition, if I take this one, this is one of the processes that is used to create nanoparticles. This is called the top-down method. Of course, this is top-down method. Mechanical attrition is a crude way of preparing nanoparticles, but it's a very effective way. We can use high pressure force and then plunder a solid body into smaller particles. Okay, then you don't have the control on the particle size and shape also. You get a distribution of particles with different sizes. But typically mechanical attrition, which is the top-down method, right? Now I told you have two ways in which nanomaterials and nanostructures are prepared. One is the top-down approach, the other one is the bottom-up method. Okay, the bottom-up. The thin film growth method is a bottom-up method, and preparing nanoparticles by solution method is also bottom-up. In certain cases, most of the nano electromechanical or micro electromechanical device fabrication consists of both the processes. You prepare something by the top-down method, or you make a thin film by the bottom-up method, then you use the top-down approach to create this nanostructure. So sometimes you have a combination of both. We'll look into those interesting examples, but this is a top-down method. It's an easy way of, you take a solid body and just plunder it and get down to micron or submicron sized particle size. So typically in this way, you can get particle sizes from anywhere from 200 to 250 microns. Now, the same solid MgO is obtained in powder form with particle sizes ranging from 50 to 250, and similar thing happens in the case of aluminum oxide also. Now, you mix it up. When you mix up, what you have is you can physically bring particles of magnesium oxide and aluminum oxide together. Now, we can perceive the same kind of reaction that's going to happen between two solid pieces of two different compounds. Now, imagine now you can make the reaction to happen between individual smaller particles of magnesium oxide and aluminum oxide, right? So, this way, see, this is now a particle, this is also, this is B, this is A. Now, you are looking at a particle of, say, 25 microns. Now, instead of making a reaction to happen between macroscopic solids of magnesium oxide and aluminum oxide, by virtue of reducing their size, right, we can make a reaction happen between individual particles. Of course, this requires, the first step is to get the smaller particles of both the compounds by mechanical attrition, mix them up, physical mixing up, so that you make sure that at least one magnesium oxide particle is surrounded by few other aluminum oxide particles and vice versa. Then when you subject this mixture to a high temperature reaction, right, don't you think that the reaction will be much faster here, right? It's the same thing that happens here, migration of magnesium ions to the other particle and vice versa. So now, instead of limiting this reaction at this interface, right, see, in this case the whole reaction is limited to a very small surface area. Now you're increasing the surface area, hence you're making the reaction to happen between large number of individual particles. So this way you can achieve the final composition within a few hours, just a few hours. From a number of years you can get down to a few hours, a few days in fact rather, because this is a 25 micron particle. If you make a small calculation with these kind of diffusions, right, it still takes a few days. So to make a solid state material like this in its bulk form, it takes a few days, 2 to 3 days to in some cases a week to 10 days. But can you further reduce this time and make this reaction to happen within few hours? Is it possible? It is possible. If I have, if I completely atomize it, and this particle I just break up into individual atoms, right? Or I take it down to nanometric scale, right? Atomization is a process that happens in thin film growth, the bottom up approach. Okay? So the process of thin film growth that involves breaking up of the solid state material into individual atoms or even smaller clusters, right? Now imagine now if you have a 25 nanometer particle instead of 25 microns, the reaction gets completed within few minutes even. So if you start with a magnesium aluminum oxide as a solid bulk like this, and if you want to transform it into a thin film, right, within 20 minutes you can get a crystalline thin film, because you're just breaking up magnesium aluminum oxide into individual atoms. So reaction between individual atoms or small clusters, the diffusion process, so you're looking at the diffusion process between in bulk, surface, and between grain boundaries. So in which case the grain boundaries are more. Again, I come back to that and try to impress upon the fact that if you have large number of grain boundaries, the diffusion is much faster. Obviously here, there's only one grain boundary here, right? There's only one boundary that separates these two compounds, and I have increased the number of grain boundaries here. See what happens in the process of diffusion. At 1000 degrees centigrade, okay, the intermigration of ions happen from one side to the other, okay, and there's another thing that we have seen. As you decrease the size of a material system, what do you see? We see more and more number of atoms sitting on the surface. The percentage of surface atoms becomes more, is it not? So the percentage of surface atoms of this solid is much less compared to when the solid is broken down into smaller particles. Now, when you have many number of atoms sitting on the surface for a given energy, the thermal energy of 1000 degrees centigrade, okay, so you'll first start seeing the surface atoms gaining that energy, and they start becoming mobile, right? So this mobility of the surface atoms is much more here compared to this case. So 1000 degrees centigrade, if 1000 degrees centigrade of thermal energy is provided to the solid pieces here, and the same 1000 degrees is provided to these smaller particles, right, you'll see more of surface melting here, because you have loosely bound surface atoms in this case. Okay. So you will see what is called a surface warping, surface melting. See, the surface melts first, right? The thermal energy that you provide first affects the surface. It starts with the loosely bound atoms. There are more number of loosely bound atoms on these smaller particles. If you go further down, if you go to the nanometric size, right, you have 40% of the atoms sitting on the surface. So the reactivity is much faster. That's why I told you, even in that case, you do not need 1000 degrees centigrade. We have seen that, right? With the decrease in particle size, the thermodynamic property that gets affected is the melting point. The melting point of a compound drops. You have seen that in the case of a refractory element like tungsten, whose melting point drops from 2200 degrees centigrade to almost 50%, 11,100. This is just amazing. So you can make the reactions to happen at a much faster rate and within shorter times, right? You got it? A bulk compound where the diffusion process is slow, and because the surface energy available for the reaction to happen between these two species is very limited, you're increasing the surface area by cutting down the size. So the process of diffusion is faster. Moreover, if you want to fuse these particles together, right, it's much better in this case than it would be in this case, because the number of surface atoms is much more here, and this number is much larger when you go down to the nanoparticle region. So in a thin film growth, it's actually an atomic process. You just break this solid material into individual atoms or small clusters. Now you can imagine if you have a cluster of or individual atoms, right, forming a new phase is much easier. It just happens in a few minutes. So if I make a superconducting compound, that takes about 7 days, a week, to prepare it in a solid state form. So you get these particles, and finally, to grow a solid state material into a thin film form, you need to get it in a compact form. Is it not? Even if you have to do a physical property measurement, it has to be in a compact form. So most of the ceramics are obtained in powder form. And how do you get this compact? You take these powders, right, compact it with high pressure, and then you have to make these particles to coalesce. They have to agglomerate. Otherwise, you don't have density on the bulk material. So this process of coalition happens at elevated temperatures, at higher temperatures. So it's a surface melting that happens first, leading to particles getting attached to one another, and since you have a large number of these particles, okay, so you have a number of nucleation slides. So the nucleation starts there. So a few number of particles coming together, and you have a nucleation. So a multiple number of nucleation sites, and these nucleation centers start growing. But as you can see, this growth is actually impeded when this particular growth of this region comes across the region where the neighboring nucleation center starts growing. So it actually gets impeded there, right, leading to the formation of grains and grain boundary. So this is a grain boundary, and this is a grain. I mean, that's why we call these bulk materials as polycrystalline So if you actually look at the microscopic picture of this bulk material, it consists of a large number of grains and grain boundaries. So a grain is a single crystal. So if you look at the microscopic view of a grain, you have a perfectly aligned, arranged unit cells, right? So a grain is a single crystal in itself, okay? So each of these grains, so the neighboring grain also is a single crystal, but the problem is the grain boundary, the region that separates two single crystalline regions, need not be single crystalline. So it's actually, the grain boundary is a defect region. So what can you have at the grain boundaries? You may completely have atomic termination of the grain boundaries. You don't have the regular formation of the lattice, okay? And the grain boundary width plays a very important role. See, grain boundaries are not required for device application. Suppose I have a solid disk like this with the presence of grains and grain boundaries. I said grain boundaries are defect regions, and if this solid disk has a property of has a dielectric property, and I can make a capacitor with it, okay? But because of the presence of these grain boundaries, the grain boundaries can act as leaky paths. So if you make a solid state capacitor with such a system, you only end up making a leaky capacitor because the grain boundaries are leaky paths. They can provide leaky paths. The charge leaks out. But if you convert this solid, this polycrystalline material, into a single crystalline thin film, right? So you do not have, you can avoid the formation of grain boundaries. So if this solid material has to be considered called a single crystal, how many grains it would have? It will have a single grain, right? So if this is a solid I have, and if I call it a single crystal, so from this end to that end, I have a perfect periodic arrangement in all three directions without any atomic termination, defects, etc. Okay. But a polycrystalline material that's made by the solid state reaction method that I have described here, you always end up getting, you might end up getting higher densities of the order of even 95% of the theoretical value. But the remaining 5%, goes into the formation of grain boundaries, which are defect regions. Okay. Now, when I give some examples, I have talked about it already. Now, suppose we have a multilayer. Again, going back to the same ferromagnetic metallic layers, and this I said is an insulating barrier of 10 to 15 angstroms thickness. Two ferromagnetic metallic layers, artificially grown layers, separated by a very thin insulating barrier, which is of the order of 10 to 15 angstroms. So, this forms a typical magnetic tunnel junction. I'll explain how this magnetic tunnel junction works, but we have seen the creation of such structures. Such structures can be created on a given substrate. I grow a single layer here, then intermediate layer and the top layer. And I also mentioned that in order to grow high quality thin film layers with these dimensions, right, the surface quality has to be very good. So, you need extremely smooth surfaces. You do not require corrugated surfaces in such cases, in such applications. No? I said you need to have surface roughness of the order of 3 angstroms. 3 angstroms gives you what is called a atomically flat surface. Right. Now, what do you have here? The insulating barrier, which is 10 to 15 angstroms in thickness, is exactly like a grain boundary. It's an artificially created grain boundary. Look, if I deposit a thin film of say 2 micron on a 2 micron by 2 micron area, okay. So, this is say a ferromagnetic metallic thin film, and when I am passing a current through this, it's metallic, it has certain resistance, right. It offers and you read a resistance value of R1. But if I create a grain boundary, what happens to the flow of current from one end to the other? A grain boundary is nothing but a defect region. Okay? So, depending on the thickness of this grain boundary, if the current has to tunnel through, right, the grain boundary width has to be of this dimension. If the grain boundary widths are like what you find in the case of polycrystalline systems, in a polycrystalline system, the grain boundary width could be a few microns. Okay? So, if the grain boundary width is a few microns, or even if the width is in submicrons, still a current cannot tunnel through, is it not? So, ideally, if I create a very narrow grain boundary, I will then be able to make the electrons to tunnel through, and I create what is called a tunnel resistance. So, case 1, I measure the resistance of a thin film layer of a ferromagnetic metal without the presence of a grain boundary, I get R1, and then I create an artificial grain boundary and get a value R2. The value of R2 with the presence of grain boundary is always greater than that of R1. You know why? By creating this grain boundary, you have created a tunnel barrier. When charge carriers tunnel through this barrier, they experience an additional resistance that's called a tunnel resistance, right? Of course, the tunnel resistance arises only when the electrons tunnel through. For the electrons to tunnel across this barrier, the barrier width has to be of the order of 10 to 15 angstroms. So, you get a nice smooth film, a single layer, using one of the best techniques. And how do I create this grain boundary? Well, you can think of creating a track, remove certain atoms. It's simple, is it not? Say if this is a layer imagine I create a track like that. What is meant by creating that track? I just removed a few layers of atoms. I can do it by electron bombardment, bombarding with X-rays, bombarding with an ion source. So this is a technology that's used in creating artificial grain boundaries, because you cannot create a grain boundary whose width is in the nanoscopic range easily. You have to go for the fabrication method. So you get a regular a single layer film, right, and selectively remove a few atomic layers. So how many atomic layers have to be removed in order to get to this range, right? 2 to 3 unit cells have to go, right? Now to remove unit cells within 10 to 15 angstroms, you need a beam which is of that size. So you need a focused electron beam or a focused X-ray source. So you can selectively etch out, knock off atoms. And this can also be done with a bunch of high energy ions. Okay? This is called the ion bombardment process. A controlled way of bombarding a surface can create these kind of trenches. Now I have a ferromagnetic metal, and an insulating barrier. This is one way of doing it, right? The other way is, so this is also a grain boundary. So a grain boundary of this nature helps in the fabrication of what is called a magnetic tunnel junction. This is very nice, right? Now, where are magnetic tunnel junctions used? These tunnel junctions, where the process of tunneling of electrons from one side to the other through this barrier, right? And during this process, if you also, while the electrons are tunneling through the barrier, you study the behavior with the presence of a magnetic field. And you get 2 resistance values. And these 2 resistance values, the difference in resistance is called a magnetoresistance. And a simple property of magnetoresistance is used by creating these tunnel junctions, artificially created tunnel junctions. And these MTJs are used in the read and write heads in computer hard drives. The whole computer hard drive technology is driven by the magnetic tunnel junction technology. It's a very involved process. It involves the process of fabricating these high quality layers and then fabricate them into these smaller junctions. Of course, in the actual MTJ process, which is the magnetic tunnel junction that is used in read and write heads, something else is involved. This is only as a concept I told you how to create an artificial layer. But actually these kind of layers are used. So it's you grow a first layer which is ferromagnetic metal, another ferromagnetic metal on the top, and you have an insulating barrier, right? It's exactly equivalent to this, right? You have a ferromagnetic metal on this side, ferromagnetic metal on the other side. Separating these two is an insulating barrier. So this is an artificially created grain boundary. So you need grain boundaries for certain applications like this. Today, the MTJ technology, the read and write heads, after fabrication, the width of the read and write head is 40 nanometers. That's the kind of technology we have reached. No? So that means the point that is used to write on the magnetic disk is just 40 to 50 nanometers across. That's the reason why we are able to pack more and more information on a given square inch of a magnetic medium. All right, yeah. So all this boils down to all this discussion now. So a polycrystalline system where the diffusion is very slow, you can enhance this diffusion if you get it in reduced dimensional form and submicron level. If you go to the nanometric scale, thin film growth process is a nanometric scale process because you completely atomize everything. You just break a compound into individual atoms. So when you break it into individual atoms, the reaction between individual atoms is always much faster. So, a bulk material that takes about 10 days to prepare, you can prepare the crystalline form of this bulk material within a few minutes. Okay. Now, if you look at this one, now you look at this. So this is log of d versus 1 by t. So you get to study the activation behavior of diffusion. D is the diffusion coefficient or diffusivity. Now diffusion happens, I told you, much faster through grain boundaries. Now, if you look at this, the first line there, the second one, the third one, you have this one representing the surface diffusion, the grain boundary diffusion, and the volume diffusion. So it goes in that way. The surface diffusion is always faster, the grain boundary diffusion comes in between, and the lattice diffusion. Lattice diffusion means it's a volume diffusion. It's a much slower process. Okay. Now, in the nanometric form, see again, did you understand now? If this is a solid material, this is a polycrystalline material. It consists of large number of grains and grain boundaries, right? So if a diffusion has to happen, the diffusion process happens through the grain boundaries. Okay. Now, typically in this case, the particle sizes will be of the order of anywhere from 50 to 250 microns. But if the same solid is made with particles with a size range between say 20 to 40 nanometers, you expect much faster diffusion here, and this is proven. This is proved now. You study the diffusion process in nanoparticles compared to submicron sized particles. The diffusion in solids consisting of nanoparticles is much faster because of this reason, all that we have seen just now. Okay. All right. Yeah, I think I have shown you this picture several times. This is a typical textbook picture of a solid state material which is in its polycrystalline form. You see the different sizes of the grains and the grain boundaries. You see well defined grain boundaries. So you take these powders, compact them, heat the powders to very high temperature, and the process of coalition leads to the formation of these grains and grain boundaries. It's the best example. So you take this solid and use one of the thin film growth techniques like sputtering, say, where this solid material is broken up into individual atoms, and then you make these atoms to rearrange and form the lattice on a support which is substrate. This is what you get. Now you get a smoother film, right? You have seen this example also, or you can get a nanostructured film like this, right? Okay. Now each of these, I told you yesterday when I showed the same picture, each of these mounds is like a quantum particle, quantum dot. So each quantum dot is highly crystalline. Okay. So this is the advantage of using thin film growth techniques, where you start with a solid which is a polycrystalline solid material, and you can transform it into a smooth, highly crystalline thin film, or into a nanostructured form. Don't think that nanostructured formation means crystallinity is lost. No, it's, see, what is the similarity or difference between these two? Don't tell me it's just the color. In this case, see, we can call both the cases as a polycrystalline material having large number of grains and grain boundaries, a nanostructured thin film again having nanocrystalline grains and grain boundaries. But these grains are orderly, right? The distribution is very narrow in this case compared to what you see here. And the problem in a polycrystalline material is you also have the formation of these voids. There is nothing there, right? The voids are, deadly for any device application. And when you transform this into, again, between these two steps, there is also an intermediate step where you get a completely smooth thin film. Okay, that picture is missing here, but you can transform this into a completely smooth crystalline thin film with a surface roughness of the order of 3 angstroms. That's not a problem. Okay, and you can transform it into a nanocrystalline form also. So the similarity is the picture that you see here, the right bottom, which you call it a nanostructured thin film. It has smaller grains, also large number of grain boundaries. In fact, the grain boundary volume is much more here compared to this case. So any diffusion that has to happen will be much faster in this case than the other case. Now, how do you judge if this particular structure is crystalline or not? So if you look at the cross section, this is what you see, right? This nano mount sitting on a surface. If you look at the cross section, that's what you see. So you need to go and do electron diffraction and look at the cross sectional TM and confirm that these nanocrystals are indeed crystalline. I mean, to call them nanocrystals, you must do electron diffraction and transmission electron microscopy to confirm that these, small quantum dots are indeed crystalline. So it involves a lot of work. You have the polycrystalline material, use the thin film growth process, get it into a nanostructured form, and do electron diffraction, and microscopy plays a very important role. In addition to, of course, crystallography. The X-ray diffraction technique is a technique that has to be used on a regular basis. Okay. Any questions? Okay, we'll continue this tomorrow.